In this next sequence of lectures, we're going to narrow our attention down to a specific kind of matrix called a vector. Now, if you've taken a physics class or maybe a trigonometry class, these are exactly the same vectors you learned about there. So at first, these are going to be a tool that let us talk about matrix equations more effectively. But as we get further into the class, you'll see that they're also useful and interesting tools in their own right. Now, in matrix terms, a vector is a two-dimensional matrix where one of the dimensions is 1. So these matrices, for example, where the column dimension is 1, that is, they have multiple rows and one column, is what we would call a column vector. And these vectors, where the row dimension is 1, are what we would call row vectors. So we can create a connection between vectors, and most often we'll use these column vectors, and geometric points in the plane. So for example, the vector u would be equivalent to the point 6, 2, and v would be paired with -3, -5. Now visually or geometrically, we represent a vector by putting its starting point at the origin and drawing an arrow out to the endpoint. So u and v, for example, would be represented like these vectors. Now, with these conventions in mind, the set of all two-dimensional vectors, like the ones we're looking at here, where the two values can be any real number, represent the entire plane, which is what we denote with this R2 symbol. Okay, so suppose we have two vectors and we want to add them together. So to see how this works, let's start by visualizing the two vectors. I'm going to put them both in the standard position where the endpoints are at the origin. So to see the reasoning behind our addition rule, think of the vectors as paths that you're walking along. So for this sum, you would start by walking to the end of the 4, 5 vector. Then from there, follow the second vector by going 3 units to the right and 7 units down. Now we can represent this by relocating the second vector so that its starting point is at the end point of the second vector. And we'll define the sum of the two vectors to be a new vector that goes from the origin of the first vector to the end point of the second one. In other words, one that follows this path. Now, mathematically, hopefully you can see pretty quickly here, the new vector's components are just the sum of the corresponding components from the original vectors. Or to generalize this, this is going to be our procedure, our rule, if you will, for adding two vectors. Now, if we reverse this process, and let's say we add the first vector onto the end of the second, notice that we get a parallelogram. Right? It's a parallelogram whose diagonal represents the sum of the two vectors. And this is why this vector addition rule is often referred to as the parallelogram addition rule. Now, finally, we'll define multiplication by a scalar by just multiplying each term by the scalar. So this has the geometric effect of stretching or shrinking the vector by a factor of the magnitude of c, and a negative scalar is just going to reverse the direction of the vector. So let's look at an example here. Say I want to combine these two vectors together. First, I'm going to apply the scalar rule. I'm going to multiply all the terms of the first vector by 2 and all the terms of the second vector by -4. So the vectors become 8, 0, -4, and -12, 8, 20. And now I can add them together just by adding their components. 8 plus -12 is -4, 0 plus 8 is 8, -4 plus -20 is -24. And that really is all there is to scalar multiplication and addition of vectors. So far, my original examples were in R2, right? My vectors were two-dimensional. My second example there on the last slide was in R3, because they were both 1 by 3 vectors. And we can extend all of these things by analogy as far as we need to. Right? If we talk about a vector with n rows, and we let those n entries each be any real number, we end up with what we call Rn. Okay, so we've got some properties, right? So some basic algebra rules for vectors. You should look through these. These all really just mimic the properties you're already familiar with from multiplication and addition. The first property here, for example, u plus v equals v plus w, that just says that vector addition is commutative. The second property says vector addition is associative. The third one says there is an identity element for vectors. It's the so-called zero vector. That's a vector where if we add it to another one, we get the original vector back. It doesn't change anything. We're going to denote negative u, so kind of think of that in terms of subtraction, by negative 1 times the vector u. And if we add u to negative u, we get the zero vector. So now we have an arithmetic identity element. Right? For every vector, there is another vector, or if you add them together, you get 0. And the rules on the right-hand side, these just establish some basic scalar rules. We've got a couple of distributive properties in the first two, and an associative property with the third one. I'm not going to prove any of these. I encourage you to give proving them a try. The proofs really all just are based on the definition that says we add, to add two vectors, we just add their individual components combined with the corresponding properties of real numbers. Okay, so we've got a bunch of definitions here, right? We've defined a vector. We've defined Rn, an n-dimensional space, and we've defined a basic arithmetic, a basic algebra, if you will, on vectors. In the next lecture, we're going to take the next step where we're going to bring this back around to matrices and see how we can use vectors to kind of streamline the way we talk about the matrix equations we've been talking about in the lectures that came before this one.